Okay, yeah, good morning, early risers. I'm Dan Frost. I'm the president of the European Association of Geochemistry, and it gives me great pleasure to start this session with the introduction of the 2024 EAG Harold Urey Medal Lecture. So Harold Urey, I'm sure everyone knows, was a physical chemist whose work on isotopes and the discovery of deuterium earned him the Nobel Prize in 1934 and led him on then to have some of the first theories about planet formation and the origin of life. So Harold Urey was a true pioneer of our field, and the EAG has named its highest honor after him for people who have made outstanding contributions over their career to geochemistry and to our broader scientific community. So it is my really great pleasure to present this award to Janne Blichert-Toft. Hold it together. Maybe you can lift it. One more applause. Put your hand on there, yeah. Okay. Applause. Is that one more applause. You take that now. Okay, thanks. I don't know how the applause will come out on the photo. I hope it does. That would be really nice, yeah. So Janne will receive her medal. There's a medal that comes with it as well. She'll receive that later today in the plenaries. And I now invite Steve Mojszis to tell us more about Janne and the outstanding contributions that have earned her this really prestigious award.
We're here today to honor Janne Blichert-Toft, a transdisciplinary scientist in geochemistry, geochronology, isotope, radiogenic geochemistry, and many, many other fields. Janne is a research director at the CNRS, at the Laboratory of Geology of Lyon, at the École Normale Supérieure de Lyon in France, where she has spent most of her career. Janne, forskningsskabende så mærkelig som menneskes, den kan aldrig forudsiges. I'll tell you what that means in a moment. But it has nothing to do with the fact that she is the recipient of the Harold Urey Award, except for the fact that that is a Danish quote from her favorite author, with some modification. Janne has published over 233 papers. It's an avalanche of science, beginning with paper number 1 here that she wrote with Chip Lesher and the inimitable Minnick Thorleif Rosing in 1992 on the tertiary East Greenland macrodike complex. Here's a picture of the lovely area of East Greenland, and that quote that I gave you is a slight alteration of a piece from the famous Danish poet Sture Ditlevsen. So I'm trying. You can tell me later. I think maybe a little bit of Gammeldansk would help in the pronunciation of that one. But the fate of research is as strange as that of humans. It can never be predicted. And one could not predict the trajectory of our medalist based on this initial publication, owing to the diversity of topics that she has explored. Not only has she spent most of her career at Lyon, but prior to that, of course, she was at the University of Copenhagen, where she received both her master's and PhD degrees. Much time was spent in those years also at the Lamont-Doherty Geological Observatory of Columbia University. And I would like to note that Janne was one of the first to win a Marie Curie postdoctoral fellowship. that was established by the European Council. She was appointed to the research staff of the ENS Lyon in 1997, corresponding to the first time that we visited one another in Tucson. We met together at a Goldschmidt meeting. So it was precisely that month, at that Goldschmidt meeting, where we observed Minnick Dorleif-Rosing, a Greenlander, for those of you who know, nearly melt because of the heat of Arizona, but also that we spent an amazing time together having dinner at the Llanos restaurant in downtown Tucson. That was a marvelous evening. And we've been friends, of course, ever since, despite that enormous bottle of Dom Perignon that we shared. She defended her HDR at the University Claude Bernard Lyon 1 in 2000. Janne is an innovator. Janne is an explorer. She's first and foremost a geochemist, which is how we've come to honor her today. But furthermore, as I mentioned, her expertise ranges into radiogenic and stable isotopes, which you'll hear more about in her award lecture. She has an exhausting catalog of research achievements, from geochronology, terrestrial and planetary mantle crust core evolution, mantle dynamics, geochemistry, crustal growth, lithospheric dynamics, ore geology. Lately, she's explored new topics in anthropology, geoarchaeology, numismatics, and ancient history. So laudations are many. Fellowships in the Geochemical Society, the EAG, AGU, MSA, Royal Danish Academy of Sciences, recipient of prizes, medals, and awards from CNRS, the Academy of Sciences of France, EGU, and so forth. Well, congratulations, Janne, for a well-deserved award, and we look forward to many more productive years from you in friendship and in respect and gratitude. We all agree, I think, that well-deserving of the Harold Urey Award 2024. Thank you so much.
Well, thank you, Steve, for this uncharacteristically brief introduction coming from you. So I am going to read my response to Steve, because otherwise I will forget some important things. So I have written it down. So, Mr. President of the EAG, Dan Frost, members and fellows of the EAG, colleagues, friends, family, ladies and gentlemen in this room, it is with great pleasure, pride and humility that I stand here today to receive the 2024 H.C. Urey Award from the European Association of Geochemistry, an association dear and close to my heart that I have served almost continuously over the past many, many years. I am profoundly humbled to be honored by the EAG and join the ranks of the impressive list of distinguished past recipients of this award, going back all the way to 1990, which was the very year that I started my own PhD, and some of whom are in the room today. I am overwhelmed by the groundbreaking science in the field of geochemistry that the Urey Award recognizes, and how, by way of this reward, I am now linked to the preeminent American physical chemist Harold Clayton Urey of, among other, atomic bomb and Nobel Prize fame, and considered one of the founders of the field of isotope geochemistry, and as such is known to every isotope geochemist. Moreover, EAG was one of the first professional societies I joined 35 years ago, AGU being the first 37 years ago, while still a graduate student, and the Goldschmidt conferences were, in addition to fall and spring AGU, the first international conferences I attended, back then at a freeway junction at Western Virginia. So it is very special, symbolic, and meaningful to me to be honored today by the EAG, especially as a European scientist at a European venue as beautiful as Prague. We have come a long way from Goldsmith's early days at the infamous Virginia Freeway Junction. So I have many to thank, but I can't do it individually. So here goes. I would like to sincerely thank the EAG, the Urey Award Committee members, my nominators, my employer, the CNRS, for daring what at the time, back in '97, seemed a great leap, a great risky leap, to hire me in France, but which almost 30 years later has honored me with some of its highest distinctions and its ultimate promotion. My host institution, the École Normale Supérieure de Lyon, for having stood by me ever since it first hosted me for my Marie Curie postdoc in '94. My second home, Rice University, for having so warmly adopted me into their Earth and planetary science family. My kind, generous, talented, and brilliant students and postdocs who never cease to amaze, awe, and inspire me by their achievements, their creativity, intelligence, and scientific rigor, and who have brought me as much as I have tried to bring them. Our outstanding, helpful technical staff, very talented, in particular Philippe Toulouk. We will come back to that later at the very end of my talk. And my wonderful colleagues and collaborators all around the world, many of whom have become close friends over the years. Steve is one example. I would not be the scientist I am today without each and every one of you. Lastly, I am forever grateful to my parents and my husband, Francis Albaridi, in case, without whose combined wisdom, integrity, and boundless love and support, no matter what, I would not have made it this far intact because, as we all know, being successful in academia is a long, bumpy road and a tough challenge at many levels, and not only for women, not anymore. On that note, I will, in the lecture that follows after this, reflect more or less seriously on how today ever came to be, because I, like many of you, I'm sure, have always been in the audience when one of my heroes received this very award, or any other major award for that matter. But never did I think that one day it would be me standing here. I assure you, it really never occurred to me, although that doesn't mean that I didn't dream about it. Which explains why I literally almost fell off my chair when I opened what I thought was just another email from the EAG, of which I get many for other reasons, and then read the incredible, but at the time surprisingly low-key statement that the EAG would like to award you the 2024 Urey Award. So I had to read that more than once before I believed it. So how did that happen? To try to understand that, I will go back to the beginning, and that is what my lecture will be about. My beginning, beyond my PhD, was the advent of multiple collector inductively coupled plasma mass spectrometer, the way it unfolded in Lyon, France in the mid-90s. I will attempt to extract the most important lessons learned from 35 years as a geochemist, and a female one at that, in the hope that despite the generational gap, my experiences, albeit gathered in a pre-DEI and pre-ADME2 world, might help guide students and early career scientists in today's research environment, which is no less challenging today than it was 35 years ago, notwithstanding the rise of especially DEI. That said, I would like to make it clear that DEI always existed, just not as the formal enforced concept it has become today, but simply it was there as a spontaneous, common sense, decent behavior it was supposed to be. In closing, I stand here today with mixed feelings from the fulfillment of a rewarding career crowned today by the Urey Award to a certain measure of wistfulness that the journey is getting closer to its conclusion, even though I still have another 10 years or so left. But mostly, though, I feel the enjoyment and deep happiness of the presence of all of you in the audience here today, despite the early hour on a Monday morning. That says lots. Symbolizing also one of the unique privileges of our job, no frontiers. So, thank you, Mr. President. Thank you, EAG. Thank you all again so very much from my heart for this exquisite and unique honor. I am truly grateful. so as you probably all know, this is the title of my talk. Alice told me that I needed to have a serious title for my talk, for the program. But this is what the title really should have been. But Alice wasn't happy with that, so I changed it. But I kept the slide. So once I had decided that I wanted to become a geologist at the age of 18, who knows what they're doing when they're 18, rather than becoming a medical doctor, which is what I was supposed to be. And I decided that I wanted to do a PhD in geology, which of course quickly veered into isotope geochemistry. Step number one was to find myself an advisor or advisors, which I did without hesitation, even though both of them today, when they learned about the Urey Award, they both told me, Janne, what were you thinking? And given that I'm standing here today, I think my thought process was not too far off. So that was step number one. Step number two was to find a hot PhD topic that sets the world on fire, that would set the world on fire. I loved my PhD. I had a great time, and I was very proud of what I did, but it did not set the world on fire. So this is just for the benefit of the young people here in the audience. This is how I wrote my master's degree in 1989. I had to write a real master's degree, a real thesis back then. One step up from my manual typewriter, it was a gift from my grandmother. And the word processor there was not very fast because you had to wait for the ink to dry before you could type your correction. And then, thank God, 4 years later, this wonderful technology had arrived, the Macintosh, with 512K floppy disks, which unfortunately went for backup, which unfortunately went mute very often. So this was just for the benefit for the young people in the audience. I'm sure that my own generation, you have been through the same trauma. So the first lesson that I learned, that in retrospect, was that your PhD does not have to define you. So then you try again. Step number 3, use your postdoc to set the world on fire. But that looked like an uphill battle from the very outset because Claude Allegra, the absolute ruler, we called that enevældig in Danish, of geochemistry in France, where I was working, his comment was, come on, surely Mojszis is not going to buy a machine just to do hafnium isotopes. Well, yes, actually, he was. But as we all know, since later, this didn't last long. But this was actually what it was all about. He was not happy. And then, of course, who I really had to convince was John Patchett, aka Mr. Hafnium, the world authority on hafnium isotopes at the time. John Patchett told me, this is a pointless machine, you're just wasting your time. And then finally, Keith O'Nions, who was the reviewer of my Marie Curie application to get a fellowship, he wrote in the review I got back, this project can't be done. The project was the only project that the only thing you could propose at the time if you wanted to work with hafnium isotopes. You have to start by benchmarking the isotope system. So I had to measure hafnium isotopes in chondrites. It had never been done. And I agree, it looked like it couldn't be done. And Keith O'Nions was not convinced. But thank God, he then wrote, he concluded his report with, but let her try anyway. So that's how that happened. So then, just before Christmas, literally on December 23rd, as is very typical for these mass spec companies, they delivered the legendary VG Plasma 54, the world's first commercial MC-ICP-MS, to Lyon. And it turned out to be a game changer. But it took a little bit, and so 3 years of very hard work, and 3 years later, the world was on fire. And so now it was open bar. Once the separation chemistry and mass spectrometry techniques and the chondritic benchmark were in place, the door was now open for the lutetium-hafnium decay system to reach its full potential as a geochemical and geochronological tool. But like every analyst in this room will know, just because you figured out how to measure chondrites doesn't mean that you know how to measure anything else but chondrites. And as it turns out, just like every cocktail requires its own recipe to be a good cocktail, then each mineral and rock type required its own specific chemistry protocol. So there was still much work and troubleshooting ahead for years to come to explore this new isotope system. And so I will show you a few selected highlights from the very, very early work to tell you what we did. The first thing I turned my attention to was to set up the lutetium-hafnium geochronometer. Theoretically, in theory, it should work because garnet loves heavy rare earth elements, but it doesn't have any particular affinity for hafnium. So garnets will have very high lutetium-hafnium ratios, and so they will grow in radiogenic hafnium very quickly. And so even for very young rocks, they will help you get very precise isochrones if you also analyze some clinopyroxenes and some whole rock together with the garnets. And so I was specifically addressing, for starters, the controversy at the time of whether burial and uplift are episodic processes or a continuous process. And as you can see, what we found here was that we found discongruous ages that started out very, very young in the western part of the Alps and getting older as we moved towards the eastern part of the Alps, showing very clearly that the high-pressure alpine metamorphism was not a single episode that took place some 120 years ago, but was a much more recent continuous process. Next thing that was irresistible once you knew how to measure garnets was, of course, the majestic Himalayas. You know, how can you not? So what I wanted to do was to date the collision, the continental collision of the Indian continent under Asia. It was not known at the time. There was a large variety of ages from very old to very young. And I dated it to 55 million years. And it was important to know this date because the collision between these two continents that led to 8-kilometer high mountains was not nothing, and it actually caused changes in the motion of entire lithospheric plates. It caused dramatic changes to sedimentation, faunal distribution, ocean currents, and so therefore to climate itself. So the next place we went was, in both sense of the word, another hotspot, a hotspot in terms of being a hotspot for science, but also a hotspot, Hawaii. And a lot of radiogenic isotope work had been done in Hawaii, lead isotopes, strontium isotopes, neodymium isotopes, but not yet hafnium isotopes. So there was a fantastic framework in which I could test hafnium isotopes and try to see what it would tell us. And for the first time, if I could produce hafnium isotopes, for the first time, neodymium isotopes, which was the only refractory radiogenic isotope system we had, could be plotted against another refractory isotope system. So we could perhaps get some new information. And we already knew from a few samples that John Patchett had already, and Tatsumoto had already measured for a few basalts, that there is a correlation between neodymium and hafnium isotopes, and there is, and this is what we found. But what we found in Hawaii was that the correlation between hafnium and neodymium isotopes is excellent, but it had a shallower slope than the overall mantle crust array. And the reason for this is the so-called Zircon effect, because the big majority of the hafnium budget is held within zircons. Zircons are heavy minerals that drop out of the sedimentary system on continental shelves, and then a bit more fine-grained sediments travel out into the deep ocean, and those sediments will have almost no hafnium, but they will have the normal rare earth element budget, and the rare earth elements will not be fractionated. So you will end up with high lutetium-hafnium ratios for totally normal samarium-neodymium ratios, and therefore you will get very radiogenic hafnium for a normal neodymium isotopic composition, which explains why this array is being rotated. It is being rotated because this plume, the Hawaiian plume, is tapping some very deep source in the mantle, and so obviously we could only conclude that there was material that had once been at the surface of the Earth in the deep Hawaiian mantle source. And this is what has caused the rotation of this correlation. And even more dramatic was the correlation between lead isotopes and hafnium. You see this extremely well-defined dramatic hyperbola, which testifies to two-component mixing between what we call the Kea component, a normal mantle component, and another component which we call the Kulau component, because it was the Kulau samples that has most of that component in it. And that component is characterized by very high hafnium lead ratio and unradiogenic lead. There you go, once again, fingerprint for hydrogenous sediments. So here we have the silver bullet, or the last nail in the coffin for the recycling of the oceanic plates into the deep mantle. And this came basically hand in hand with Rob Vanderhill's famous pictures, seismological tomographic pictures at the time, where we see the plates plunging way into the deep mantle. So this seemed to be just the right time for this kind of thing to happen. Then, of course, with the MC-ICP-MS came high sample throughput, which for a TIMSS person like me, and for most of my PhD, I was a single collector TIMSS person. This was just heaven, especially because the high sample throughput did not come at the expense of high precision. The precision was the same, but instead of spending 6 hours on one measurement, you spent 20 minutes. You have to run a few more standards, but it pays off well. So then we started, when we realized that, then we started to sweeping all the Earth's ridges and hotspots, plumes, including the Hawaiian drill core that dated from the late 90s, early 2000s. And we made a lot of measurements in order to try to get a better handle on the length scales and residence time of heterogeneities in the Earth's mantle. Of course, I cannot go into any details of this for you today, there isn't time, but that was the main idea. And of course, we had some brilliant students who accompanied me on this work, so that I had a few slaves with me in the lab to do that many samples, and some colleagues who came along with their morphs and orbs, and it was delightful. We had some good years in Lyon doing that. And so, but we didn't stop by young basalts, because I have always been fascinated by chromatites. I think it's the coolest rock type in the entire terrestrial rock record. I always loved chromatites. They always fascinated me. And so this is just a few select lutetium hafnium isochrones, and I just put that up there to brag, because chromatites are almost more difficult than chondrites to measure. They're really difficult to measure and get the data right. And so this was some of my most challenging work, was working on chromatites, but also some of the most fascinating and satisfying. And I was so fortunate that I got to work with two of the world's chromatite experts, first Nick Arendt for many years, and later Igor Puktel for many years, and still today. And so with of course all of these isochrones, thanks to in great part to Igor Puktel, are matched with congruous samarium neodymium. I did a few of those, but Igor did most, and Igor did all the rhenium osmium isochrones. And so with this framework, we have been able to use the lutetium hafnium ratio as a tracer for the very early Earth. And here you can see each of these points is not one sample. Each of these different colored points is a lot of different chromatite samples that we have taken the mean value, and it each represents a different chromatite emplacement. And from that, we have been able to glean a lot of things about fractionation processes in Earth's, in the primordial terrestrial magma ocean, and even come up with timescales for mixing in the Earth's mantle of the order of about 2 billion years, which goes hands in hand with the average age of oh yeah, I forgot to say that the average age from lead isotopes that we got from the Kulau component in Hawaii is 3 billion years, which already there tells you that plate tectonics must have started very early in Earth history, and we get the same picture when we study chromatites. So then like I said, yes, we bought the machine not just for lead isotopes in the beginning, but Francis can never sit still for very long with the same thing. So we decided, let's take on hafnium isotope cosmochemistry to benefit from the improved analytical precision and accuracy that we had now and the big throughput that we had. So we went back to basics to redefine the benchmarks of lead isotopes, old ideas with a new twist. And here are the founding papers for high precision, high throughput lead isotope analyses using thallium doping and sample standard bracketing, MC-ICP-MS, now everywhere in every lab in the world, I think. We revisited the solar system primordial lead and redefined a more precise value with Nantan. And we defined for the first time the solar system thorium-uranium ratio, which had not been measured so far. We also dared to try to measure the age of the solar system, which was reserved only for TIMSS people, because TIMSS people did not accept the unacceptable error bars that you get from MC-ICP-MS. But we did get the same age, and our error bar was not that bad, and this was a long time ago. And we also dated the age of Earth's earliest building blocks at 1.2 million years. And I supported this absolute lead age with the relative age from the hafnium-tungsten isotope system, because once you figure out how to measure hafnium isotopes, well, then you can also measure hafnium and tungsten isotopes for the short-lived isotope system. And so therefore, we couldn't help getting involved in the controversy at the time of whether the age of the moon and the terrestrial core formation was at 30 million years or after 60 million years, so early or late. And we found that it was early at about 30 million years. And so the second most important lesson when I look back today at what I have learned from the last 35 years is to keep an open lab as opposed to work secretly. Keep an open lab, invite everybody, work with everybody, teach what you know to everybody. An open lab, and now I am going to use my best DEI language, attracts motivated scientists and students, bringing about a creative, inspiring, trusting, educational, collaborative, and safe environment, which in turn catalyzes the pursuit of the best science. And this was something that we did before DEI, even existed as DEI, like I said earlier. And I can only recommend it. And so Alice also told me that I'm supposed to come with some sort of conclusion. So my conclusion is that MC-ICP-MS opened up the entire periodic table to isotope geochemists and helped bring isotope geochemistry to other fields, just like bells. If you stay in the room for the rest of the day, you will see exactly this picture. And bells, I am grateful that you allowed me to crash your session. We have never collaborated together directly, but our paths have crossed. We are from the same generation. Our paths have crossed many times as editors or reviewers or just scientific discussion in the hallway at a meeting. But you should know that I have always admired you from afar for the very creative science that you have always done, but also for the very rigorous analyst that you are. I know that when you have been an editor of some of my papers with methodologies in them, whew, So, this is why when I saw there was a session from you, I said, this is where I want to be today. This is my way of honoring your legacy. And what it also did was opening the door to the great joy of engaging in interdisciplinary research. And I will let you deduce from yourself what that really means. So my last two slides will be, if I still have time, my core team for the last more than 30 years, Philippe Teluc, whom many of you know, an exceptional, well-renowned ICP-MS engineer. He can make any machine work, whether it's a car or a TIMSS or an MC-ICP-MS or an ICP-MS, that's Philippe. And Francis Albarete, heroic firefighter, fearless firefighter, 2 times academician, and a world-renowned geochemist. And this picture was snapped by a journalist in 1992 when our lab burned down. It wasn't our fault, we were cleared, but we were almost put in prison for a while. And the firefighters, they came. Actually, their firehouse is just on the other side of the street, so they came really quickly. But they didn't want to go in because they asked, this was the year after 9/11, and it was the year after there was an explosion in Toulouse, which was a chemical explosion. So they had had enough by 1992, so they figured out very quickly by asking us what's in there. And we said, well, there's HF, there's perchloric, And then they said, no way, we're not going in there. So then Francis went in there without anything and then put out a lot of the fire, and I went in there with him. I was handing him the big red things to take out the fire. And then we came back out again to get some air, and then the firefighters suggested that they could equip Francis, and that they did that, and then he went in and put out the rest of the fire. And then this picture, it was in the newspaper the next day because the journalist thought that it was a real firefighter. And then when the fire was out, all the firefighters, the whole team, went in with their hoses and everything, and then they ruined whatever little was left of our lab. And that was it for at least a year or so. So this is all the wonderful students and postdocs that have made my life so brilliant for the past 30 years. They have been, a light in my everyday and in the lab. The red names are our students from our own school, and all the yellow names are all the students that came from everywhere else. And the postdocs all came from everywhere else. They have their own color. And I owe all of them so much, and I am grateful to them. And since I haven't been stopped yet, I did have a last slide, which is that the lutetium-hafnium system, to be my fate, it was meant to be, because it is literally the French-Danish connection. I am Danish, and I ended up working in France. Hafnium is called hafnium because it was discovered in Copenhagen in 1922, although it was already predicted by Mendeleev in 1963. So don't come here and tell us that research and theoretical science is not either correct or useful. And so because it was discovered in Copenhagen, the Latin name for Copenhagen is Hafnia, it was named hafnium. And lutetium was named after the native city of its discoverer in 1907, who was called Urey. And he came from Paris, and the Latin name for Paris is lutetium. So there we go, the French-Danish connection. Thank you very much for your attention.
Thank you very much, Janne, for a very inspiring talk, and congratulations from all of us. Please thank Janne again. We have time for questions.
So Janne, you dated or you analyzed everything or nearly everything. What you wish you could analyze if you could have a wish?
What I didn't analyze and I would like to analyze now? Oh my God, I haven't thought about that. I don't know, maybe more chromatic ice. I know it's maybe a bland answer, but if it's something that I love and that fascinates me, and there's still much more to find out, just ask Igor. We're only 10% through if you ask Igor.
Janne, thank you very much for this wonderful journey that you took us on. Since we have time, I'd like you to dwell a little bit deeper into the neodymium versus hafnium initials that you get from those chromatides. And what you were alluding to, mantle heterogeneities, mixing, but I'm so intrigued by that mismatch of hafnium and neodymium.
Yeah.
It keeps me awake.
I know.
We've got experiments going at 5 and 7 GPa, and we just can't get our heads around it.
Right. Right. As you could see, first of all of the chematioids I've been working on are, Igor assures me, and he is the one who sampled the samples himself, they are the best preserved, most pristine. So that is dealt with, okay? We don't have to worry about that. So yes, so as you could see, many of the chematioids actually lined up nicely on the terrestrial evolution curve. And so that is just like, looking at neodymium hafnium correlation today, everything is fine, you don't worry about it. What is really interesting, of course, are those chematioids that fall off the terrestrial evolution curve. And those are the ones who are testifying to the very early fractionation processes in the terrestrial magma ocean very early on at very high pressure. Okay, so this is when the lutetium, hafnium, and samarium, neodymium ratios do not fractionate the way they do in MORB and ORB in the same direction, but in opposite directions. And so then you get, a decoupling between the neodymium and hafnium isotope correlation. And so this is, and if they all fell on the terrestrial evolution curve, we wouldn't learn anything. But because we have some of these chematioids that fall off, and some of them falls off dramatically, this is calling. We need to have some different fractionation process, different mineralogy at very high pressure. So this is why we're calling upon this happening in the primordial terrestrial magma ocean. And of course, the chematioids that are the most dramatic in this way are also the oldest ones. But then we have some of the ones that gets into the Proterozoic, and they begin to fall below rather than above. And so that starts to tell us something else, something about plumes that are much more like what we have today at that point. So everything that is decoupled is what really teaches us something. So yes, it keeps me up at night too, but for a good reason. It's positive. It's positive. It teaches us.
Thank you so much. Any more questions? Let's thank Janne again. Thank you so much.
Thank you.